This is Lab 7, Section M07 by Pouria Hosseini, curving motion. The purpose of this lab was to analyze the curving motion of a sun around a black hole. The goal of this lab was to estimate the mass of the black hole by observing the motion of the sun. So I used a model created in VPython to track the motion of the sun, which was given to us in an Excel spreadsheet. And with this motion, we were able to determine what the mass of the black hole was. And the model created, variation on the momentum principle was used. You can see that here. This variation separates perpendicular and parallel aspects of the motion. This is generally used with curving motion, and the momentum principle and curving motion are applied to this problem in order to estimate the mass of the black hole. So if we go ahead and run this model, it'll show us, you can see the sun goes around the black hole. You can see from the model the force of gravity gets larger as the sun gets closer to the black hole. The force in the perpendicular and parallel direction both get larger as it nears the black hole, and then they decrease as it moves further away. So to run through everything in the code that I've changed, I added a black hole, as you can see here, and the mass of the star was 1.989 times 10 to the 30th kilograms. Delta T was set to be 1 day in seconds. You can see that here. The position of the black hole was given through WebAssign, and you can see that there. Here you can see the formulas that were used to calculate dp dt and the parallel and perpendicular portions of dp dt. So here's the parallel one right there, and this is the perpendicular one right there. You can see r is the distance between the black hole and the star. That was done just by subtracting the positions. And then this line right here gives you the mass of the black hole based on the last point that the loop runs. So at the last point, it takes the force and multiplies it by r squared, and then divides it by the gravitational constant and the mass of the star, which should give you the mass of the black hole. So if I go ahead and run this here, give it a minute. There we go. And now you will see that the mass of the black hole is given as 2.985 times 10 to the 31st. So for the what does it mean question, I'm going to go ahead and run this model one more time. And as you can see, this model shows us 3 arrows. One is Fnet or dp over dt. The other is Fnet or dp over dt in parallel, and the other is Fnet or dp over dt in the perpendicular. Now technically, the model shows dp over dt in the parallel and perpendicular direction, not Fnet. Now these quantities are the same in value, but what they represent are slightly different. Fnet represents the force that is acting on an object. dp dt is simply the change of its momentum over time. So you can calculate what the forces acting on an object are by measuring its change in momentum over its change in time, because that's the effect that the force has. But they're not exactly the same thing. The force is what causes the change in momentum, even though they are the same in value. So the what if question asks, if the black hole was switched with another black hole, assuming everything else remains the same, including the motion of the star, and gravity is still the only force acting on the system, could the black hole possibly have a different mass? The answer is no. If the black hole had a different mass, the force would change. The mass of the black hole is included in the formula for the force, and if the force changes, then the acceleration that the star undergoes changes, and that would make the motion of the star uh, change.